Hello everyone, welcome back to our PySpark interview series. Today we're diving into a fundamental topic: what is a data frame in PySpark and how does it differ from an RDD? If you're exploring PySpark or preparing for interviews, understanding the distinctions between data frames and RDDs is crucial. Data frames bring powerful SQLite capabilities to PySpark, while RDDs offer flexible, low-level control. Join us as we break down these two core concepts and explore why data frames have become the go-to for big data processing in Spark. Definition: a data frame in PySpark is a distributed collection of data organized into named columns, much like a table in a relational database or a data frame in Python's pandas library. This structure allows you to work with data in a clear, organized way, with each column representing a specific attribute. Data frames offer a simpler, higher level abstraction than RDDs, making them easier and more efficient for processing structured and semi-structured data. Data frames were introduced in Spark 1.3 to streamline data handling in Spark applications, and they quickly became the main way to manipulate data. This is because they make it simpler to query and analyze data while also benefiting from Spark's optimizations for speed and scalability. Key characteristics of a data frame. Schema. Data frames come with a defined schema that specifies column names and data types, which makes them well suited for handling structured data. This schema allows you to interact with data in a clear, organized way, as each column has a set data type, making it easier to validate, query, and manipulate the data effectively. Optimized execution. Data frames benefit from Spark's Catalyst Optimizer and Tungsten execution engine, which optimize query planning and execution. The Catalyst Optimizer evaluates how best to run your queries for maximum efficiency, while the Tungsten engine boosts performance by improving how the data is managed in memory. Together, these features make data frames highly optimized for speed even with large data sets. Ease of use. Boost. Data frames offer a high-level API that simplifies data manipulation, making it easy to perform common operations such as filtering, aggregating, and transforming data. You can even use SQL-like queries to interact with the data, allowing those familiar with SQL to get up to speed quickly with data frames. Compatibility. Data frames support multiple data formats including CSV, JSON, Parquet, and ORG for both reading and writing. This compatibility enables smooth integration with various data sources and simplifies moving data between Spark and other data processing or storage systems. These characteristics make data frames an efficient, user-friendly option for structured and semi-structured data processing in PySpark, offering both flexibility and performance. Differences between data frame and RDD. Schema. Data frames come with a defined schema that includes column names and data types, making them ideal for structured data where each column has a specific role. RDDs, on the other hand, have no schema, which makes them better suited for unstructured data where there's no predefined format. API. Data frames offer a high-level SQL-like API similar to the one in Pandas, allowing for easier, more intuitive data manipulation. RDDs provide a low-level functional API that requires custom transformations, giving more control but demanding more code and setup. Performance. Data frames benefit from Spark's Catalyst Optimizer and Tungsten execution engine, which optimize execution and memory management, resulting in faster performance. RDDs lack these optimization layers and execute operations as defined without additional performance enhancements. Data processing. Data frames are best suited for structured and semi-structured data, such as data with rows and columns. RDDs are more flexible with unstructured data but lack the efficiencies data frames bring for structured formats. Memory management. That data frames use optimized memory management through serialization techniques, allowing for more efficient storage and handling of large data sets. RDDs access memory directly without these optimizations, which can lead to higher memory usage. Data sources. Data frames can read from multiple data sources such as CSV, JSON, Parquet, and OR, making it easy to integrate with various data formats. RDDs have limited built-in support for data sources, which may require additional code to read data from certain formats. Ease of use. mm, Data frames are easier to use with high-level IPs and support for SQL-like operations, making them accessible even to those with minimal coding experience. RDDs are more complex, requiring custom functional transformations for most operations. Transformations. Data frames support complex SQL-like transformations out of the box, which simplifies data manipulation. RDDs require explicit functional transformations for each operation, making them more flexible but less user-friendly. Interoperability. Data frames integrate seamlessly with Spark SQL and MLIP Spark's machine learning library, making it easy to switch between data manipulation and analytics tasks. RDDs have limited direct support for SQL-like operations, which can make them less convenient for certain analytics tasks. Lazy evaluation. Both data frames and RDDs support lazy evaluation, meaning they build a logical plan of transformations without executing them immediately. This helps in optimizing the workflow by executing transformations only when an action is called. These features illustrate how data frames and RDDs each bring unique strengths. Data frames simplify structured data processing and perform better for SQL-like operations, while RDDs provide a more flexible, low-level API for unstructured data. When to use data frame vs RDD. Knowing when to use data frames versus RDDs in PySpark can help optimize performance and streamline data processing. Data frames are ideal when working with structured or semi-structured data, such as data organized into rows and columns, because they come with a predefined schema and support SQL-like queries. With data frames, you get the benefit of Spark's built-in optimizations thanks to the Catalyst Optimizer and Tungsten execution engine, which make data processing faster and more efficient. Data frames are also well suited for tasks that involve Spark, SQL, or MLIP, as they integrate seamlessly with these libraries. On the other hand, RDDs are preferable when you need low-level control over data transformations, particularly with unstructured data that doesn't fit neatly into a schema. RDs allow for greater flexibility, making them useful for custom data processing tasks where data frames' higher level abstractions may be limiting. While RDDs don't offer the same level of optimization as data frames, they give you direct access to Spark's functional API, allowing for custom, fine-grained transformations that might be necessary for specific applications. In short, choose data frames for performance and ease of use with structured data, and RDDs for flexibility and control with custom or unstructured data workflows. Practical example. This example demonstrates the process of creating a data frame in PySpark, performing a filtering operation on it, converting it to an RDD, and then performing further transformations on the RDD. Let's walk through each step in detail. First, we start by creating a data frame using a list of tuples with employee data. Each tuple contains a name and a salary representing individual employees. The spark.createDataFrame function is used to turn this list into a data frame with two columns, name and salary. Data frames in PySpark are a convenient way to work with structured data since they allow SQL like querying and provide column based operations, making data manipulation clear and efficient. Next, we apply a filter operation on the data frame to select employees whose salary is greater than 4,500. The filter function allows us to specify this condition, and PySpark will efficiently process only the rows that meet it. After filtering, we use select name to choose only the name column from the filtered results. This selection is useful when we only need specific fields for the next steps. The show function then displays the resulting data frame with the names of employees who earn more than 4,500, such as Alice and Charlie. Following this, the example converts the data frame to an RDD by accessing the .rdd attribute. This transformation is beneficial when we need the flexibility and low-level control that RDDs offer for custom transformations. Once we have the data frame as an RDD, we can apply RDDD operations on it. In this case, a map transformation is used to extract only the name value from each row, essentially producing an RDDD that contains only the names of employees with salaries above 4,500. The collect action is then called to bring the results to the driver program as a Python list. Finally, the list of names is printed showing the employees who meet the salary condition. This example highlights how we can switch between data frames and RDDs in PySpark to leverage the strengths of each, using data frames for structured data processing and optimize SQL-like operations, and RDDs for custom low-level transformations when needed. And that's a wrap on data frames and RDDs in PySpark. I hope this video helped clarify what makes data frames different and why they are often the preferred choice for handling structured data in Spark. If you found this explanation useful, please hit the like button, subscribe for more PySpark insights, and don't forget to click the notification bell so you never miss an update. Thanks for watching and see you in the next video.